Guess it should be on. Okay, good. Yeah, great. So now we really talk about energy conversion, and the two methods that I described briefly were using phase transformations with ferromagnetism and also using phase transformations with ferroelectricity. So you have to understand that at some point we need simple enough models that we can actually design devices. So there's a lot of open questions here about how one would relate the quite sophisticated or quite detailed models of phase transformations that I described in the last lecture to these much simpler models. So there's a lot of kind of heavy modeling going on here, and we really need some more mathematical viewpoint of some of these simplifications. Basically, relations between models on different scales, or modeling detailed domain structure phenomena versus overall phenomena. Okay, so the point is not to have an electrical generator. Oops, we're so we began talking about models of ferromagnetism together with phase transformation last time. I'm going to use those models, and then we'll talk about the two methods. So let's talk about the materials first. I mentioned we discussed models and examples of materials that have ferromagnetism and phase transformations, and what seems the most, or what seemed to us the most promising systems to look at are so-called Heusler alloys. So Fritz Heusler was a German mining engineer, actually belonged to a mining family, but was not very interested in mining, but more interested in science, and he discovered Heusler alloys. I guess the first Heusler alloy was, they all have the chemical formula A2BC. And I think the first Heusler alloy was copper 2 manganese tin. So in the periodic table, copper, manganese, and tin are not ferromagnetic. But if you make copper 2 manganese tin, it's a fairly strong magnet. So he was interested in this phenomenon, and now there's lots and lots of Heusler alloys, hundreds of Heusler alloys, and there are different kinds of Heusler alloys, and they're very much studied because of this propensity toward ferromagnetism, because of the interest in the basic physics of where does the ferromagnetism come from. In fact, it comes often from the manganese atom. But also they're very rich in not only magnetic properties, interesting magnetic properties at low temperature and so forth, but they also have many phase transformations. So it's a good place to look for possible materials to do ferromagnetic energy conversion. And we were looking at these materials. They also have quite rich behavior. Recall these diagrams I was writing where I put the temperature axis vertical. And then we have a Curie point for the austenite phase. That's where we begin to see magnetism. It's a second order phase transformation. And then it could transform by a Martensitic phase transformation to a Martensite phase, which may or may not be ferromagnetic. I was discussing the sensitivity of magnetic properties to the lattice parameters, which change here, meaning that many different possibilities could occur. For example, so this one has exhibit. This is a way you would usually see this. You would put a small magnetic field on the specimen. So actually the values of this magnetization mean nothing. It's just the transitions that you see here in this kind of measurement. So this is the Curie point. So that means the austenite, as you cool it, this is temperature, as you cool it, ferromagnetically orders, and then you see this Martensitic phase transformation. So that has this kind of diagram. In this case, the Martensitic phase transformation is almost on top of the Curie point. So you could even say, effectively, the austenite is non-ferromagnetic. It transforms to ferromagnetic Martensite. This is a particularly interesting case that caught our attention. Also, it's very interesting from a material science viewpoint because it has this diagram. It has no ferromagnetism. So the austenite is not ferromagnetic, and the martensite is not ferromagnetic. But here's a measurement, and it's quite interesting measurement with a very strong field. So this is 7 Tesla. That's a huge field. You need an enormous magnet to make a field like that. Or it's the kind of field you get inside MRI. Then you suddenly see that it develops this very strong, it develops phase transformation to a very strongly magnetic state. Okay. However, if you do tests without that magnetic field, you won't see any magnetism. So that's the correct diagram. So what can happen, of course, and what's happening here, is that the Curie point is of the austenite phase is below the transformation temperature of the austenite-martensite phase transformation. So of course, so the austenite, if you somehow could stabilize it to lower temperatures, you would see it ferromagnetically ordered, but you don't see it ferromagnetically ordered because it transforms already to martensite. But as I mentioned a few times, and it's in the models I discussed before, this temperature can't be changed to at least to first order. It's a second order phase transformation, so cannot be changed. And if you want to think mathematically of, in a very simple way of convex hulls of multi-well energies, that's the way you would argue this, is this temperature is not changed, effectively not changed, or at least to first order, by applying a field. But this temperature is changed, can be changed quite significantly by applying a magnetic field. So the first order phase transformation temperature can be changed by applying a magnetic field. So mathematically, you have this multi-well structure. In the models I presented yesterday, the applied field supplies an energy minus h dot m integrated over omega. H is the applied field. So of course, that's a linear function of m. That tips the energy up and down, and you can tip it so you can bias towards one of the wells and change. So if it's biased like this, and so it's no longer at the transformation temperature, and now with the bias, you now change the temperature. Of course, the wells go up and down with temperature too. So you change and now we have this new transformation temperature here. It's a very geometrical way of thinking. So anyway, what these guys have done is they've moved, by applying this enormous field, they've moved the transformation temperature to below here, and then suddenly you see this strong magnetism. So it's all, from a mathematical point of view, it's all about wells going up and down, adding energies, to bias wells up and down, which is what I was doing in the last lecture when I detuned that crystal as well. So that's the story. However, when you look at this, and actually a former postdoc of mine, Vijay Shrivastava, he realized immediately that if that's the case, you should be able to move this TCA above the theta C by also changing composition, because that also moves the wells up and down. So he had some good intuition about how to change the composition of this material to move TCA above, and he got this material. He was also trying to make lambda 2 equals 1, and this particular alloy has lambda 2 quite close to 1, but there's also room for improvement. So this could be made more reversible, probably by further compositional changes. But anyway, this is the behavior. So it has a fairly small hysteresis, maybe about 6 degrees hysteresis. Magnetization versus temperature. So now you can see it's been stabilized. So the martensite phase is non-ferromagnetic, and now it transforms to the austenite phase without any strong field. So this is just by changing the temperature. There's no applied field, and now we have this strong martensitic phase transformation. And then the austenite phase here is ferromagnetic, and if you continue raising the temperature, you reach the Curie point somewhere up here. Okay, so that's a quite interesting material for energy conversion. It has the right properties. The austenite is ferromagnetic, but not only that, it's actually quite strongly ferromagnetic. So this unit invented by Faraday called EMU per centimeter cubed is very high. So that's about the magnetic strength of iron at this temperature. So it's a strong magnet. It's also a soft magnet, which is quite interesting. Magnetization, so you take this material, it depends on which phase. So now we could take the temperature over here, or we could take the temperature over here. So in the higher temperature, we would be in the austenite phase. And so, you know, with a very small field, a few Oersteds, it magnetizes a lot. In the martensite phase, it's non-magnetic. Okay, there's a whole story about that, but anyway, that's the situation. So in fact, even with a very small applied field, we get quite a good size fraction of the total magnetization. It's also shown up here. So with 0.05 Tesla, that's a very small field. We're already up here. 0.5 Tesla, we're up here somewhere, and 1 Tesla, we're up there. That measurement is done under an applied field. Those measurements, anyway. As I mentioned, you know, you could think. So this is again a whole series of open questions. You could think that if your free energy not only depends on deformation gradient, but also depends on magnetization, then the whole thing about lambda 2 = 1 and supercompatibility and low hysteresis goes out the window, because this material's magnetic. It has magnetic energies. You know, there's divergence-free conditions of magnetization, so forth. So we don't know anything about that, basically. But the observation is it matters very little that you also have magnetization. One would think it should matter. From a theoretical point of view, the energies are quite large, but it seems that the compatibility conditions, ignoring magnetism altogether, are still relevant for magnetic materials. For example, in this nickel-manganese indium system, or nickel-manganese tin, this is a tuning. It's been tuned by lowering. This is hysteresis versus composition, replotted hysteresis versus the middle eigenvalue. And you see again the sharp drop. It only goes down to 6 or 8 degrees hysteresis. So this actually has been, in fact, made smaller. I don't have the latest graph here. So it's even gone down to 3 or 4 degrees, which is typically the best we can do, or maybe 2 degrees in some bulk materials. And so those are the nice calorimetry graphs showing this is heat flow versus temperature, as I already described, showing the peaks due to the latent heat of phase transformation. Heating and cooling, and you can see the small hysteresis. And okay, so this is a little demonstration my students did. They had a little copper finger here that they're heating, and they put this nickel cobalt manganese tin alloy on top of that. That's that specimen, and just heat it up. And so you go above the phase transformation temperature, it becomes strongly magnetic. So this material is a material that you put on the table. It's non-magnetic. You're just below the transition temperature. You heat it up 6 degrees, it becomes a strong magnet. You let it cool down, it's non-magnetic again. Okay. So that's this demonstration. So this went above the phase transformation temperature, and actually you can kind of see it follow the lines of force over onto the permanent magnet as when it becomes magnetic. Someone pointed out to me that if I took this whole demonstration and I turned it 90 degrees, it would be an example of energy conversion, because it would be the conversion of magnetic energy, or energy released in phase transformation, into potential energy in that case of a gravitational field. But of course that's a kind of silly way to do it, and this is a much better way. So what you should do is you should take a piece of nickel cobalt manganese tin and put it on top of a permanent magnet. So the role of the permanent, and this permanent magnet doesn't have to be a very strong magnet, but the role of the permanent magnet is as I was showing before, this material is quite soft. So, if left alone to itself, it will just demagnetize itself. Okay, the magnetic domains will form. They'll all cancel each other out. It won't have any strong ferromagnetism. It's a soft magnet, as indicated by this graph. But as also indicated by this graph, with a small applied field, it magnetizes. Okay, you can see that jump again. It magnetizes, so you want that to happen. So you put a permanent magnet. There's nothing you have to do with this permanent magnet. It doesn't even have to be that strong, so forth. And then you wrap a coil around it. So somehow the basic idea, and we'll go in a bit more detail in a few minutes, but the basic idea is, recall the dipolar relation. We derived that last time. Remember, that came from you taking the dipole field. From a mathematical point of view, it's singular integrals. Taking the dipole field, cutting out a little region around the dipole, and you cut it out and you modify and you take away the singularity. So you smooth the field on a small neighborhood of the singularity of the dipole, and you do it in a divergence-free way, and then you homogenize, and that gives you the B field, and the M is the magnetization, the dipole strength per volume, and if you homogenize that, you get this relation, which is fundamental to dipolar magnetic materials or dipolar ferroelectric materials, as Peter was also saying yesterday. Doesn't have any material constants in it. So anyway, it's the dipolar relation and Faraday's law that we'll use to first, in a very qualitative way, try to analyze what happens in this energy conversion device. So first of all, as you go through the phase transformation, biased by this permanent magnet, the magnetization, remember magnetization is a vector field on this configuration. The magnetization should increase suddenly. In fact, it should go up to a quite large value. That means dm dt is very large at some level, or some average of dm dt is very large. And you can see from this relation, dm dt is partitioned between dB dt and dH dt. So then the question is, how much dm dt goes into dH dt and how much dm dt goes into dB dt? That's very much the subject of micromagnetics that I presented last time. So the way you figure that out is you in the simplest way is you minimize that micromagnetic energy. And recall there was the last term on that micromagnetic energy, the demagnetization energy. That's really the key. That's the key term in deciding how much dm dt goes into dH dt and how much dm dt goes into dB dt. And it's very shape dependent. So if I have a body, and this is again related to Peter's talk about he was talking about ellipsoids and the fact that there was an n perpendicular and an n parallel, and these can change depending on the aspect ratio of the ellipsoid. That's what it's all about. So if you make the right kind of ellipsoid, a big dm dt will give you a big dB dt. And then dB dt is curl E, minus curl E. And that means that, we'll look in more detail, but that means that it generates a current in this coil. So that's the basic scheme, is we're going to go through the phase transformation temperature. It's going to magnetize, we're going to generate a current in the coil. But it's actually much more subtle than that, and now we have to talk more about models. So anyway, with that idea, I'll show a derivation of this model. Is you can develop a model of the current I of t in that coil, and I'll talk about that. Okay, so now we're at the point of, we already discussed the difficulty in understanding these free energies of micromagnetics, which included both strain and magnetization. And that was the last term I just discussed, which has the shape effect in it. And so we have to go to simpler models. And you can very formally think of of minimizing out deformation and magnetization in this complex model and getting a scalar model. And actually, it's many things we can derive directly from experiment on the scalar model. For example, the derivative of phi with respect to temperature minus the derivative of phi with respect to temperature is the entropy. And the entropy, the change in entropy in a phase transformation can be related directly to this latent heat, so the area under this peak. So somehow directly from experiment without exactly evaluating this infimum, this constrained infimum, we can get information about the derivative of phi with respect to theta. And in fact, and one expects a double or double well energy, in this case a double well energy for this phi, and many things about that we can evaluate directly from experiment using calorimetry. And the other extremely important thing in this energy conversion is the fact that I already mentioned, that was already in this experiment with this very large field, is the fact that the phase transformation temperature can be changed by bathing the specimen in a magnetic field. There's an effective magnetic field on transformation temperature, and that's extremely important in this thing. Without that effect, you'll not generate electricity by this device. So this is both experiment and theory. So when you apply a phase you apply, let's see, the blue one. Yeah. So in this particular material, it can happen that it can happen either way. But in this particular material, if you put a magnetic field on, it lowers the transformation temperature, as indicated by this graph. And from this information, you also get, and also this magnetization curves I mentioned, you can develop a free energy in a scalar model. Most simple, everything, all the space dependence is out, and just a scalar model where the free energy depends on magnetization and temperature. Magnetization is some average magnetization in a certain direction, the relevant direction for this energy conversion. Okay. So how do you then go to a mathematical model to predict how much electricity is generated? It's from Maxwell's equations, combined Maxwell's equations combined with this free energy. So let's just discuss. So we start with Faraday's law. That's the integral form of the law I already mentioned. In other words, curl E is minus dB dt. And so in the integral form, it says that the flux of B through a surface is the time rate of change of that is related to the circulation of E around the boundary. And then if you think about coils around this magnetic material, you would have a current in each coil, and so we could add up this equation for each coil, and that the end result. The left-hand side can be interpreted as the voltage at the ends of the two pieces of wire which come off those coils, which are actually joined, but I just drew them in this way. Of course, there's the permanent magnet too, which generates a constant magnetic field, and the voltage at the ends of these wires produces a current in the coils. It also could have an external resistance. So there's Ohm's law. So this is V equals I times the external resistance. That would be the load, and then the resistance in the coils is whoops, I'm losing it. Too bad. So the resistance in the coils is this resistivity rho divided by the cross-sectional area of the wire that makes up those coils. Okay. Oh, maybe I can use the other one. No. Okay. Anyway, I hope that it's clear. Okay. So now you have a current in this coil, and it produces a backfield on the specimen. This backfield, a current in a coil. This is the Biot-Savart law. Produces a backfield on the specimen. So that's a very important aspect. It's that backfield which produces the electricity. produces the electricity effectively. So that's given by this formula, where the current is, maybe I can just use the old-fashioned way here. Oh, battery's coming, okay. Good.
I think the old-fashioned way is better though.
Okay, maybe. Yeah. Okay, good. So in the meantime, I'll do the old-fashioned way. Okay. So this is the back field produced by this current. So that's effectively another of Maxwell's equations. And of course, that back field affects the magnetization. Great. These batteries don't last that long, do they? Okay. Okay, very good. Okay, I'll try this one. Oh, wait a minute. Okay. Okay, very good. Okay, so we have a voltage across the ends of this wire. We have a current in the wire, and this voltage. So in fact, I could eliminate the V between this one, and I'll do that. And this one is equal to B. Now, by this dipolar relation, B equals H plus M, we have two contributions to H. We have the contribution from the permanent magnet, which will cancel out, and we have the contribution from the back field. So you put this together. You put the V there, you put the I there, and you put the B there, and you get this relation. So you get, with these kind of simplifications, of course, there's still the main complication then is how do you get this magnetization in the specimen itself. The magnetization in the specimen itself comes from the previous slide, so it comes from this minimizing this energy. So we're going to minimize this energy to get the magnetization, apply a temperature which depends on time, and solve this equation. So this is a very simple model. It's a kind of ODE model because we have di dt is in here. I only depends on t, and the complication is in figuring out, the magnetization. So I hope that gives you some picture of the a model. It gives rise to an ordinary differential equation, and these are kind of graphs that you generate. So this would be calculated voltage versus time as you're heating, and that's the measured value, and you can generate some understanding of these of this method of energy conversion. So the backfield plays a big role, as I mentioned, and what the role it plays is the following. So as I say, the specimen starts to magnetize. It generates a time-changing B field, which generates by induction a current in this coil. And the current in the coil, in turn, modifies the magnetic field on the specimen. The magnetic field is the magnetic field of this permanent magnet. And this modification is very important because, remember, the magnetic field affects the transformation temperature of the specimen. So the presence of the back field has the effect of raising the transformation temperature on heating and lowering the transformation temperature on cooling. And that's absolutely critical because you don't produce, we know from the first lecture that the efficiency estimate that if the minimum temperature and the maximum temperature are the same, then we don't generate any work. We don't generate any electricity. So in other words, it's on this slide, is if you just went back and forth through a phase transformation, keeping the temperature the same, there would be no area in this graph. In the context of the first lecture, again, it's maybe I would need to explain this more, but you would generate no electricity. So you need to bias it so that the transformation temperature on heating is different from the transformation temperature on cooling. The backfield does exactly that. And the backfield together with energy minimization, of course. The energy minimization tells you that the transformation temperature will be different under different applied fields. So that's the basic effect. So it works well. It's actually been commercialized by a Swiss company. We tried to get intellectual property on this method, but the University of Minnesota's intellectual property office, particularly at the time, was not very good. But anyway, this Manfred Kohl's group has developed the method in a nice way. Also, in the meantime, we kind of soured on this method for another reason. Remember, I said that there's this shape effect. You want the big dm dt to give you a big dB dt. You don't want it to be all go into dH dt, because that does nothing. And I mentioned that depends on the shape of the specimen through the last term, the demagnetization energy term in micromagnetics. So what's a good shape for making the big dm dt give you a big dB dt? It's a long, thin shape, it turns out. So a pancake is a very bad shape. If you wrapped a coil around a pancake, you'd get hardly any induction in the coil. But a very long shape is a good shape, okay? So you should have very long, this phase-changing ferromagnetic material should be in the shape of a rod. But, you know, if you have a shape of a rod, it was difficult, and this is a whole aspect I haven't discussed. It was very difficult to think of a good way to do, you know, the heat transfer. You need to heat and cool this thing as rapidly as possible to get a lot of electricity, right? So that seemed difficult. And then you could say, well, that's not so bad. Maybe I could have an array of rods, you know, a whole array. And then if you think mathematically, you know, how does an array behave? And that's a kind of, you know, from a micromagnetic point of view, what's the behavior of an array of rods? You know, say like a square array of rods all parallel to each other. That's maybe good for heat transfer. Actually, a square array of rods all parallel to each other behaves more like a flat plate than it does like an array of rods, because they interact. Okay, so it turns out, so if you had a square array of rods and the average shape of it was like a plate, well, then it would act more like a plate than it would. So you would defeat the shape effect of the rods by doing that. So anyway, we're thinking about those things. We said, well, maybe ferroelectricity is better. Ferroelectricity, when you do ferroelectricity, you think in energy conversion. Instead of induction, we're going to use capacitance. So we're going to use capacitors. That's the natural way to think in ferroelectric energy conversion. And if you use capacitors, they have this big surface, free surface. They're very thin. Thinner the better, as we'll see in a minute. So you have this very big surface where you could do heat transfer. You can point it at the sun. You can do whatever. So seems like a better thing is so we started working on ferroelectric phase transformations. And the material we chose is a very readily available material, barium titanate. It undergoes a phase transformation undergoes 3 phase transformations, actually. The highest temperature one is this one. It's a cubic to tetragonal phase transformation. And it develops a polarization which is parallel to this elongated axis. So the models for these are okay. You know, I presented quite some detail the models of phase transformation with ferromagnetism. The models with phase transformation with ferroelectricity are very similar. They have that shape-dependent term. It's the same term. So the only main difference is in ferroelectric materials you have free charges. Charges can move, you know, in your system, and they can, and that requires another term of the energy, which was not in the magnetic models. There are no magnetic monopoles, so there's no magnetic free charges, and so there's a certain energy which was not included in the magnetic case that needs to be included here. If you have free charges, depends on the situation. But okay, so the idea is we use capacitance, and the main effect is we could be in this cubic phase, and we put it as the dielectric or in between the plates of a capacitor, And then when we transform to the ferroelectric phase, we get these variants. This is a cubic to tetrahedral phase transformation, so 3 variants. Like the magnetic case, there's also the plus or minus. At least in this case, there's the plus or minus invariance, so there's effectively 6 energy wells, and we discussed that in the other lecture. You might draw a picture like this. And the point about this is that when you're in the high temperature, so in barium titanate, the high temperature phase is non-ferroelectric, it's paraelectric. So there's no polarization, there's no strong polarization that's exhibited in that phase. If you phase transform and you have a voltage on the plates, it will tend to phase transform to the variant that's pictured here, which has its polarization in the vertical direction, and this will be very strongly polarized. So this will have the tendency to, as you can see from all these plus charges, to attract a lot of charge. Okay, so that's the effect we're going to use. Okay, so already I'll jump to the simplified model. So in barium titanate, we do have a quite nice, measured with great care, simplified model for the free energy. Strain is gone, so it's measured in an experiment like this kind of experiment. Maybe there are domains, maybe there are strains, but anyway, it's just measured. Just the polarization is measured, and a free energy function is fit to that data. And there's the free energy function, so we're going to use this free energy function. It's actually a triple well potential. At high temperature, there's a single well, and at low temperature, there's 2 wells corresponding to plus or minus m. And there's the form. I mean, as I say, there's great care that goes into deriving these forms. Because it's an important material. But the free energy just depends on polarization and temperature. And this is polarization in this vertical direction. So as I say. Okay. So now we can do energy minimization by hand, of course, because it's a multi-well energy. If we put it in a capacitor and we apply a voltage V, then the electric field in the capacitor is V divided by the thickness of the capacitor, and then the appropriate minimization problem for a capacitor to figure out what is the polarization is this minimization problem. So if and there's the free energy. So I guess everybody in this room could do this energy minimization, and you get, of course, you can jump from one well to another, and you do that at some Maxwell line, some equalaria line, and you get graphs like this. So you take the solution, and you compute from the solution. So the solution is E is given, and you're minimizing with respect to P. So you would naturally get, and the first derivative condition is that condition, and so you get graphs like this, as you can imagine. This would be the mixed phase region as you go across here, and if you're careful, you can invert that relation, and you get the polarization as a function of electric field and temperature. So it looks like that. Just minimization of a triple well energy. So now, how would you make an energy conversion device? It's very simple, of course. Maybe there's other ways, but the most simple thing you could do is you could take this capacitor, this ferroelectric capacitor that has the ability to really attract charge, and put it in parallel or series, I guess it doesn't matter, with an ordinary capacitor. And then you could have a load here. So, and then hook up a battery across here and charge up the system. Okay? So add charge to the top plates of this capacitor as shown here. And let's suppose we're in the high temperature phase. So this is in the paraelectric phase. There's no great tendency to attract charge. It attracts some charge, of course, because it is a dielectric. And the charge is that you've supplied to this circuit, to the top side of this circuit, is distributed between this capacitor and this capacitor according to the capacitances. So standard. So some charge may move here, some charge may move there. It depends on the capacitances. And now you cool this material through the ferroelectric phase transformation. Then it becomes strongly polarized. It really attracts charge. Charge moves from here over to this side, and it goes through this load. You produce electricity. You heat it back up, and again, so the main effect, the main important effect is the effective field on transition temperature. When you heat it back up, of course, it has a much different field inside than it did previously. So that has an effect on the transition temperature. So we split the transition temperature by the effect of the field on transition temperature. That's the most important, again, effect also in this energy conversion device. And so in the end, charge sloshes, as you heat and cool this guy, you have two temperatures. As you heat it and cool it, charge sloshes back and forth between the two capacitors, and you generate electricity. Okay, so what's the model? The model, again, very simple. At this level, very simple circuit analysis. So we take remember the polarization is a function of electric field and temperature, and it's given by this graph, and of course we can jump between one phase and another, but we're basically using this relation. The charge on the capacitor is given by this, is related to the polarization, as you can imagine, and it's given by this formula. And the charge on the ordinary capacitor is given by its capacitance. That's a constant for the capacitor times the voltage. And now you just write circuit laws. So when the charge is moving from here to there, there's a current. There's Ohm's law that says that some of that energy is dissipated in the load. And I won't write those circuit laws. The rate of change of these charges is related to the current. The total charge is constant because we charged up the two capacitors, and you can't destroy charge. Of course, we have to worry about leakage across these capacitors. If we have leakage, then we have to every once in a while recharge the thing. But anyway, that's I didn't write those circuit laws, but I think everybody in this room could write the ordinary differential equation, which comes from this and the circuit laws, and it's this ordinary differential equation. So the active material is contained in this dphi dp, and we have to be on those stable branches that come from energy minimization, and this comes from the ordinary capacitor. And then we would have, and the temperature versus time is something we prescribe. And we can think about good functions, temperature versus time. So we could go from a high temperature to a low temperature. And so you see that this is a first order ordinary differential equation, but I just prescribed two conditions. So and also I would be prescribing two conditions on the charge. And so there's a consistency condition for that to achieve those end conditions. So I'm prescribing a 2-point boundary value problem for a first order equation. So I have a consistency condition, which is that. That has a nice interpretation. So that condition says that the electric field at the high temperature and at the low temperature are related by, so this is at the high temperature, this is at the low temperature. The slope of this line is related to the capacitance of the ordinary capacitor. Okay, that's just comes out from the ordinary differential equation. So, of course, in this device, we want a very big change in polarization. So, the design criterion that comes from that is and the slope of this line is minus the capacitance of the ordinary capacitor times the thickness of this divided by the area of the ferroelectric capacitor. So you want this, if we want as big a change in polarization as possible, of course we should make the slope of this line as steep as possible. We should make a huge capacitance for the ordinary capacitor. You want to make that as large as possible. And also, of course, you would like to make D as, okay, so this is D over A. So from that point of view, okay, anyway, D over A, we can, there's many choices of the C0. Okay, so that's what one should think. And sure enough, it works quite nicely. In this demonstration, this is a single crystal of barium titanate. It has 2 electrodes on it. It was just bought commercially, and then it was heated and cooled on a hot plate. And you can see that this is the electric field according to the model, as well as measured in the experiment. This is the polarization from the model and the experiment. And this is the generation of electricity. Each time you go through the phase transformation, heating or cooling, and this is the temperature, you get a pulse of current. So there's a huge number of questions about this. I mean, even this demonstration shows that it competes favorably or even exceeds the energy produced by thermoelectric materials, which I was saying was the only real competitor, not very good competitor, but in this small temperature difference regime. So for these kind of temperature differences, this competes favorably with that. But there's a huge number of questions, and there's a whole aspect of heat transfer and so forth, which most of the questions are open with these methods. And maybe there's other methods that are sort of like this, maybe also using phase transformations. I don't know. Here's another remark is the beauty of a first order phase transformation is you just draw these wonderful squares in the mixed phase region, and they're Carnot cycles. In the temperature entropy diagram using the free energy model that I said before. Again, the entropy is defined as the derivative or minus the derivative of the free energy with respect to temperature. So Carnot cycles are possible, and there's some pictures of those would be good from the point of view of the first lecture. But also, if you look at this model, it actually has a critical point here. So this is the mixed phase region. But above the critical point, these lines are not so steep. What this means in practice is that you can make these much bigger cycles, have bigger temperature differences, so higher efficiencies, and these are not so bad cycles to use. So it seems like, and just in steam generation, people also use supercritical Carnot cycles, or supercritical cycles of this type. And it does seem like an interesting thing to do, so we're doing that. Okay, so that really gets me, and it's about time to the end of my lectures. We think that I mentioned that this is a typical solar thermal plant. People are countries around the world are building these at quite a high rate. They're getting bigger and bigger. And they use steam generation by focusing the rays of the sun on this black tank of water up here. And we think that maybe with some of these other methods of energy conversion, one could take these mirrors, distribute them around with the homes and so forth, and do a much more distributed method of energy conversion by focusing the rays of the sun and oscillating the temperature at the focal point of those mirrors. That's just one example of many things that one could dream about, and I hope some of the people in this audience take this up and realize some of these dreams. So thank you very much.
Any questions?
Yeah.
So this is related to your talk yesterday.
Yes.
So it was about, so you presented a picture where it was reversible, but not.
Yes, this is this movie. Yeah,
yes.
yeah.
And so you were heating it and cooling it, right?
Right.
So, and it was never the same.
Right.
Every time you did it.
Right.
What I'm wondering is, did you heat it and cool it slowly and see whether it was repeatable or not?
We did different rates. Maybe is it slow enough? It's hard to say. So the experiment is that there's a. Let me describe the experiment, and then maybe it can answer some of this. It's a thin plate of this special material that satisfies the cofactor conditions, and it was actually a polycrystal, but it had big grains, and we're looking inside one grain. So it's a thin plate, and it's sitting on top of a thin film heater. which was designed to make the temperature as uniform as possible. But as you can see from the movie, there was a slight bias because we always had the interface moving sort of diagonally, not always quite the same, but and one of the problems in this thing is because the hysteresis is so small, like 0.2 degrees C, that it's very hard to capture. It's very hard to control the interface in any way. I mean, we control it with a temperature. It's very hard to. I said that incorrectly. It's very hard to remove the temperature gradient that would bias the interface. So it's biased a little bit to go diagonally. The thin film heater, the attempt is to keep the temperature as uniform as possible. And in time, there was a pulse of current given. Below the thin film heater was a liquid nitrogen cooled, metal copper block. So the thin film heater would heat the specimen up, and then it would, when it was turned off, it would just cool naturally through this block. But nothing was changed. So you can see from that arrangement, it was trying to make the heating cooling rate the same periodic in time as best as possible. And so your question is if you made the amplitude smaller and smaller, right? So we did do that.
Longer.
Or the wavelength longer. That would have very little effect because most of the transformation is occurring quite quickly. So maybe we were oscillating the temperature in those pictures maybe 5 degrees C, something like that, and but the transformation was occurring. It's 0.2 C hysteresis or 0.5 C hysteresis or maybe 1 degree hysteresis. We measure various things but it's still very small. So that's much smaller than 5 degrees. So much of the transformation was occurring in a very small interval. Yeah. But it would be quite hard to freeze that interface because, as I say, the hysteresis is so small. Yeah.
So in order to use this for energy harvesting, probably you would need to do many cycles.
Yes, right, yeah.
So my question is, how fast can these materials really be? How many cycles can you do? What are the rates you can do?
Okay, so first of all, there's two aspects to that question. One is, do you have phase transformations that can be reversible with 100 million cycles? And that was, I did address that. I mean, to the extent we understand now, maybe we'll learn some important things soon, but as far as we know, that's the best way. Satisfy the cofactor conditions. And then the second thing is, you need to do it as quickly as possible. And that's a heat transfer. There's a strong heat transfer aspect to that. And this is why we like the thin film, approach. And we're in the method ferroelectric. That's why we like the ferroelectric method in some sense, is because, and we're trying to do it with, and we're not. I didn't show any data from that, but we don't have good data yet. But we're trying to do it with epitaxially grown films, which are of nanometer thickness. So really like 50 nanometer, 100 nanometer thick films, which we believe can be heated very quickly and cooled very quickly. So maybe kilohertz or 500 hertz, something like that, could be reached by that method. Of course, you have this in the analysis of that is one has to understand, and this has a big effect, is the material, each time it goes through the phase transformation, it releases or absorbs latent heat, and it takes time for that. You get that, and so it's not just ordinary heat transfer analysis. One has to take into account the fact that latent heat comes in and out of that film. But anyway, we like that. We like the flat aspect because the heat transfer could be much higher, and we could maybe do 500 hertz or something like that. And then that's if we got one of those pulses of current like we got at 500 hertz, then we have a very good energy conversion device. Yeah.
About 5 slides back, you were showing those pulses.
Yeah.
What worried me was that they weren't symmetric.
Yeah, yeah, I don't know the reason for that. That's a good question. Let's look at it again. Yeah.
There. One down.
Yeah, there's a. Yeah, even the graph is not very clear, is it? There are actually.
Oh no, wait on. The zero is.
Yeah.
Oh no, there's something very funny about.
So what is the 1? Yeah, there is something funny about the graph. Or maybe this is mislabeled actually. I don't know.
But anyhow, the pulses have got different area underneath them, and therefore the amount of charge contained in each is not cancelling.
Oh yeah, I mean it's very hard to tell. I mean they're very sharp. The transformation happens very quickly. It's actually the slopes. There's 2 slopes that are governed by the model I mentioned. So I don't remember. Yeah.
No, I meant the
yeah.
area under consecutive pulses doesn't look the same.
Yeah. So I don't like this one and this one, for
Yeah.
example. Yeah. Yeah. I mean, it's very hard for me to tell. I can maybe show you some data that's but a little less fine than this that maybe can answer that. Yeah. Yeah.
If I may, one more. So have you tried to make an estimate of the really energy efficiency of these materials, right? In terms of the Carnot efficiency.
Yeah, I mean it's of course these temperature differences are very small, so the efficiency is very low. We don't even think about efficiency as a measure for this method of any of the methods I've been discussing. We think that it's usually the efficiency is most. It was important to Carnot because he's paying for the wood that was being burned for the steam engine. We're often not paying for the heat. It's very different in that respect. So in the waste heat applications, you don't pay for the heat. The heat is free. So efficiency is not then W divided by Q plus is not so important as it would be in our current methods of electrical generation, where we use high temperatures and we burn a fuel. So in this case, even in the natural, all the methods, all the sources I mentioned, or many of the sources I mentioned, we don't pay for that heat. So efficiency is not so interesting. What really matters is your first question: power output. Yeah, power density, work per cycle, and also the per cycle volume or something like this. Those are the measures that really matter. And I wish I could. We have predictions. I don't like to put these predictions up at the present time because it's really at the beginning, and it's too dangerous. Yeah.
What is the hysteresis behavior of electrical?
Oh yeah. So I never addressed that, but and that was also a question I think at one point. Is the hysteresis, if you analyze it, which I didn't do that in these lectures. Maybe I should have. It is the most important source of loss. So really, you want to phase transformation with exceedingly small hysteresis. That is the most important source of loss. You can imagine many sources of loss. We also have, you can see it maybe in these graphs. Is there's also a leakage across the capacitor. So across the not the ordinary capacitor so much. But across the active capacitor. So making that concerns the quality of material. So leakage is also a source of loss. But we hope that we can remove that source. And then the other one is the other main one. In fact, the most important one is hysteresis. Yeah. So I didn't analyze that, but that can be shown. Yeah. Yeah.
Okay, if you have any more questions, thank you very much for these wonderful lectures.
Thank you.